Well, it makes me want, like, in a couple of years, maybe I'll just try and really just devote myself to math or something. I got some stuff I want to take care of, but then after that, maybe just, it's because there's so much, like, statistics I want to learn, and the
Yeah.
calculus and the differential equations and all this stuff. And you just can't do it with my time, limited time with my eyes and everything. You just can't do it unless you really devote yourself to it. So maybe just get the fundamentals and then try and do it if I can someday. Who knows, I guess. But it's the way it goes.
Did you ever consider coaching tennis?
I actually did. Taught some tennis, and I was an assistant coach at CU Boulder for the women's team.
Okay.
Yeah.
Because I have another session with Casey Ross tomorrow night.
Oh, dude, okay.
I was curious that if he did not have a tennis coach, that'd be an awful fun thing to get involved in.
Oh yeah, well I'm sure if he's got, I mean if you're anywhere near one of the best players, you know, I mean.
I would think. Did you have one at that age, or was your dad your coach?
No, I had a real coach.
You had a regular coach. Okay.
Yeah, how old is the guy?
16. He's a sophomore in high school.
Oh yeah, he definitely would have a coach.
Okay.
I mean.
Okay. Well, plus I'm sure that he has a coach at Kent, Denver. Their team was #1 in the state. I'm sure that they have a regular coach there. But
yeah, usually if a guy is that good, I mean, he usually has one of the best coaches in the state. You know what I mean? So I'm sure he's working with. I wonder if I would even know who it is, even though I've been out of the game here for like 20 years.
Right.
Or something. Sometimes the same guys are still.
I tell you what, I was impressed when you came up with Alan Waldman's name.
Yeah, right.
And I was more impressed that I remembered it. Because that was like 30 years ago when we used to go watch him play, my wife.
Yeah. He would beat Larry Loeb. Larry Loeb was another good guy. Larry Loeb was my coach for a long time, and I think Waldman used to beat Larry.
Yeah, Waldman had a shot that I don't remember anybody else having, and I watched quite a bit of tennis. Of course, it was all local players. I wasn't watching top pros. But he had a shot that was more like a baseball swing. The ball came off like a ball comes off of a baseball bat.
Oh, yeah, right.
I don't know if you ever watched him play, but
yeah.
Well, you probably remember that shot. And it was a two-handed shot, and I can't remember if it was from the backhand or the forehand. Because all I know is that, boy, when you watched him play and he hit this shot, it was just spectacular. It was like a bullet.
Yeah.
So many winners with that shot, yeah.
Two-hander. He had a brother, too, Corey Waldman, who was also a good player. But, yeah, there's a guy, the best, I mean, Jim Courier played a lot like that.
Yeah.
His swings were baseball.
Both swings were, weren't they? Yeah. Yeah, I just probably don't see it on TV when I'm watching it. You can't, it's kind of like going to a baseball game. When I went to a baseball game last year, and I could not believe how hard the ball is hit. I mean, when it hits a fence, it makes a noise, or when it goes back up into the stands and it hits the concrete, it's like a bullet. And you don't get that appreciation when you watch it on TV.
No, it's the same with tennis. And in fact, now it'd be like,
I'll bet you everybody hits it that hard.
Some of the top guys now, because it's like, you know, even guys in my generation, I think they're hitting the ball quite a bit harder now than they were like 20 years ago.
I'm sure you're right, just because of the technology,
Yeah, it's crazy how hard. They're hitting forehands over 100 miles an hour.
Yeah.
It serves at about 150. So it's just like kaboom.
Yeah.
Really.
I like that kaboom sound. That's what I used to like about watching Waldman.
Yeah.
All right, let's see where we left off here. I remember the problem, and I think it's no.
Yeah, do me a favor. Ask that kid who was coaching.
I will. I'm definitely going to do that. And
yeah, it could be either somebody I knew as a coach, or maybe sometimes some of the guys that were players in my era became coaches. So I might know the guy as a former player.
Yeah, I wouldn't doubt that you probably do know the guy. Hold on.
Yeah, so this guy's the best in this. Did he win state? Do you
No,
know?
he's second in the state. I looked up the Colorado rankings. Actually, he is ranked one. If you go to online, I don't know how he got to one, because he told me he played number 2 at Kent, and they won the championship last year. When I first got up and looked him up, they had him ranked number 2. So maybe he's done.
Well, he could be second on the team, but maybe he's 16, so maybe the number 1 guy is in the 18s.
Okay, so all the rankings go on age. It's not like they don't have a high school ranking.
Yeah, yeah. Because in my senior year at high school, I got all the way to the final at number 1 of the 4A, you know, and then lost a match to a buddy of mine that we used to go back and forth. And I was like, I lost that match. I was like, oh, man, of all the matches to lose, you know.
Oh, because that affected your ranking?
Well, no, it was just that you're playing for your school and everything, you know, at state.
Oh, okay.
It was the high school championships. So, yeah, it's like you got all the way up there and then, boom, lost that final one. So I was like, oh. But anyway, that's the way it goes. So.
Finally, I found this page. I could not remember which page we had left off on. Another thing I'd like to get is I'm going to ask Casey if he has any film. Maybe I won't do that. I was going to say he must have a video of him playing. It'd be fun to look at him and show it to you. Not so much for me because I don't have the appreciation of skill. But I'd love to show it to you and say, does this guy have maybe what it takes to go all the way?
Oh, I could certainly take a look, but the thing is you have to see the guys in competition.
Yeah, I'm sure. It's not just a question about.
Some guys have great strokes, but the psychological aspect, you know, you don't know if they'll hold on.
Right, and that's probably what separates the greats from the middle of the pack.
Yeah.
It's the same thing with golf. It's the 6 inches between the ears that matters the most. All right, this is the classical calculus problem where they're going to ask us to do 3 things here. One is find the area of that shaded region, R. The other is to rotate it about one of the axes and find the volume of that object. And the third thing is we're going to use this as a base, and we're going to put cross-sections on it. Compute the volume of the solid with that as a base, and the height as a function of x equal to the square of the length of the base, and so forth and so on. Let's do it one at a time here. Hold on, let me open up my Windows journal. Luckily, I have not had any problems over my last 10 or 20 sessions with, you know, that weird thing that was going on. It kept requiring me to reboot and restart.
Oh, yeah, so that's been going on.
It disappeared. I don't know what happened. All right, so what's the area of this going to be?
Let's see. All right. So the area of R. Okay, so that would be. Not the volume, but the area. I guess you'd have. I miss this. The graph of the sine of x, and then minus the graph of 1 minus.
Yeah.
It'd be sine of x to the x-axis, and then minus 1 minus cosine of x to the x-axis, basically. That's how they usually do it.
Well, the integral of a function is the area under the curve. So if I just integrated this function, I would get all the area between that function and the x-axis. Same thing with this.
Right.
So if I do the integral of y sub 1 minus y sub 2, I'll get the area of the shaded region.
Okay.
Okay, so I want to do minus this quantity, 1 minus cosine x dx. And what about
now, is that the same as saying the integral of sine of x minus the integral of 1 minus cosine of x dx?
Yes, and we're going to solve it that way. We're going to separate it into 3 different integrals in order to integrate it.
Okay.
Okay. The next question that we have to ask is, what are our limits of integration?
Okay. Well,
Because we have to go from this point to that point.
Yeah, but we don't know what that is, right?
Well,
oh, you'd have to set the 2 graphs equal to determine that
right.
point. Right?
So if I say sine x equals 1 minus cosine x, that will tell me what those points are. The question is, what's an easy way to solve this? Clearly I can see this point must be 0, because the sine of 0 is 0 and the cosine of 0 is 1. So 0 is obviously a solution.
Oh, okay.
What is this point here? We are in the calculator section, so let me go to Wolfram Alpha and show you how we would solve it using Wolfram Alpha. I could even use this other calculator, but Wolfram Alpha probably is better. Since you don't have that other calculator, there's no point in using that. If I move cosine x to the other side, then I've got sine x plus cosine x equals 1. Sine x plus cosine x equals 1. And it should give me the zeros of this function. And this blue curve is sine plus cosine, and this pink curve is the line y equals 1. So the solution lies where they intersect, as always whenever you're trying to solve that. So that's clearly at x equals 0, and that looks like, well, let's see what that solution is precisely, because they also give you the solutions. 2 pi. How is that 2 pi? That's not 2 pi. I'm a little confused here. Let's see, would 2 pi work? Yeah, it would. That would be 0 and that would be 1. So 2 pi is a solution, but there's another one right here. That clearly is not 2 pi. That's 1.57. That's half. That's pi over 2. And pi over 2 also works because the sine of pi over 2 is 1, and the cosine of pi over 2 is 0. So 1 equals 1. So our two solutions are x equals 0 and x equal pi over 2. How come that isn't obvious from, hold on. even that one doesn't give you pi over 2. Let's see. Yes, it does. This solution right here. Are you familiar with this notation? What this means is n is all integers. The subset of n is all integers. Okay? And if I let n equal 0, clearly one solution is 0.
Okay.
And if I let n equal 0 for this solution, you'll notice that the answer is pi over 2. And also, if I were to continue this curve forever, you would have solutions up here and up there.
Oh.
In other words, every pi over 2, this one plus 2 pi, this one plus 2 pi. And that's why they have two solutions here, is you have to state this solution with two different equations.
I think I get that. Okay.
Yeah, in other words, it would be 0 and 2 pi, which is up here, and then another 2 pi up here would also be a solution. And this statement right here covers all of those solutions. But the solution pi over 2, and then you're going to have 5 pi over 2, and then 9 pi over 2, also going to give us solutions, and those are expressed with this notation. Notice that if I let n count from 0 up, I will get all of those solutions. And n can also be negative. In other words, it also applies to the left side. There's all these solutions over here.
Wait, so you're adding 2 pi to each answer?
You are for this solution here, yeah, and this one. Yeah, that's what that says. You're adding 2 pi to each one. This really could have been written 2 pi n plus pi over 2. I think I would have preferred, if I was writing that solution, that's the way I would have written it, is 2 pi n plus pi over 2, which is what that says, where n's a subset of z.
Yeah.
A little embarrassing for me when I first started working with my Russian student a year ago. I pulled up Wolfram Alpha, and I didn't fully understand that notation, and he did. Because they had covered this kind of notation in Russian schools. Not so much in American schools, although they do cover it now, although I'm not sure anybody would recognize this n subset of z. Z is the set of integers right here. So, okay, so we know what to integrate from. We know to go from 0 to pi over 2. And so let's see, the first integral of that is negative cosine, evaluated from 0 to pi over 2. And then we're going to have, what's the next term going to be?
Okay, the next term, well, I guess it's minus the integral of 1 minus cosine of x, so you'd have to, okay, yeah.
Let's break it up into 3 integrals. We'll have the integral of the first term, the integral of the second term, and the integral of the third term.
Oh, yeah, right, okay, so that's the integral of, so that's the integral of 1. That's the integral of 1, which would be, so let's say, integral of 1, would be x.
Negative x.
Well, I mean, minus, yeah.
Because of this minus sign, right?
Right.
And that also is going to go from 0 to pi over 2. And then the last one is going to be plus, because we have a minus and a minus. So it's the integral of cosine of x, which is just sine of x. Okay, now let's evaluate each one.
Okay.
The biggest mistake that can be made on these kind of problems is getting the negative signs wrong. So I have to be very clear here that I'm adding that to that to that.
Okay.
So let's come up with a number for each one.
Okay, so the negative of the cosine of 0.
Well, let's start at the top.
Negative. Oh, whoops! I was going to subtract. It's that evaluated pi over 2 minus it evaluated.
Right.
Okay, what am I doing? Yeah. Okay. Okay. So negative the cosine of pi over 2. So let's see. That pi over 2 is 0,
okay.
So it's negative of 0.
So there's a 0 goes there, and then we're going to subtract
minus cosine of 0, which is 1. So we have minus 1.
Well, now here's where, yeah, it's minus a minus 1.
Minus a minus 1.
Right, that's what I'm saying about these negative signs. They can really get out of control, where if you don't use your parentheses and brackets right, it's very easy to get very confused.
Okay. Yeah, I would make a mistake.
So I'm going to add to that the middle term. Let's put parentheses around that. And that's merely minus pi over 2. Right?
Yes.
Okay. And then I'm going to add to that the last term, which is 1. 1 minus 0. This is actually minus 0 also, just for understanding purposes. Okay, now if we add all of those together, we get 1 plus this one, 2 minus pi over 2. And let's hope that's a positive number, because we know it needs to be a positive number. And it looks like it is. Pi is 3.1, so this number is less than 2. So actually that's the answer that we would want to give, yeah, in terms of the area of R. It doesn't say convert it to a decimal or anything like that. Okay, now how do we find the volume of the solid that is obtained by rotating that about the x-axis?
Okay. Now I remember something about it. You have to use, this would be like washers, right?
Yes.
You have to use washers.
Yes. In other words, if we attempt to draw a picture, it's going to end up looking like kind of an open flower. If you look at it from this direction, it would look like a flower. Okay. So what is the volume of this thing using washers?
Okay. Yeah, I don't hardly remember how to do these at all.
Okay. Think of, first of all, how are we going to position the washers? Are we going to position them vertically or horizontally?
I would think you'd want to do them vertically.
Right, because this first one right here, there's no hole there. If it's small enough, there actually is, but there's no point where there's no hole. But the next washer, you're going to position here, and there's going to be a hole right there.
Right. So it's the big radius minus the small radius.
Exactly. Okay, so we're going to integrate along the x-axis, and we're going to go from the same 2 points, 0 to pi over 2, and next we have to figure out what the volume of each of those washers is, because that's what we're doing when we integrate, is we're summing up all of those washers as their thickness goes to 0.
Okay.
So what is the volume of a washer?
Well, it's the, I'm thinking the big radius minus the small radius, the radius of the hole.
Okay, if I draw a washer,
Yeah.
and we think of this as having, that's just from the top view, but if we think of it having a thickness,
Yeah.
then the volume is the area
Right.
of the washer, the outside, that's pi r squared, minus the area of the inside, which is pi little r squared.
Right.
So that's the area of the shaded region. And then we're
I was going to say,
go ahead.
Yeah, go ahead. Yeah, I was just going to say that has to be multiplied by the thickness, right?
Right. In other words, we then multiply by the thickness, and the thickness is dx.
Okay. That's where I was getting confused. It seems like dx is being used as something to multiply it by, but it's also integrated with respect to. You know
Well,
what I mean?
here's
So,
how, yeah, let's talk about dV.
Okay.
The volume of each of these washers is pi r squared minus pi little r squared, all multiplied by dx. And you can think of dx as being a ½ an inch thick, a ¼ inch thick, a tenth of an inch thick, or approaching 0. This formula is correct, and so to get the volume of a washer, I'd need to integrate it. Integrate both sides. That's how you end up getting this formula. I can remove the pi. I can factor the pi out, leaving the inside r squared minus little r squared.
Now, when you integrate both sides, are you integrating both sides with respect to x then? So you get on the left, what would you get?
Oh, that's a very good question. If I put this back into a differential equation, it's this. Dx equals pi r squared minus pi little r squared, okay?
Okay.
Now, if I integrate both sides, this is something I've never really been able to answer. I'm not sure how you can integrate the left side with respect to v and the right side with respect to x, but you can do it. And so if I integrate both sides, what I have on the left is v, and what I have on the right is the integral of pi r squared minus pi r squared dx. So that's the microscopic way of looking at it. If we look at each washer and try to figure out what dV is, which would be the incremental volume of a very, very thin washer, and then to get the total volume of the washer, we would integrate that. But regardless, we end up with that. In other words, whenever we're trying to find these volumes of objects of rotation, we integrate with respect to a certain axis. It doesn't always have to be the x-axis, it can be the y-axis, but in this case, washers work perfect as long as the skinny section is always the D variable. In other words, the skinny section in my picture here tells us that we're going to integrate it along the x-axis. If I were to somehow draw my volume this way, my washers, then I would be integrating along the y-axis.
Yeah, right. Okay.
Okay. So this is relatively straightforward also. Again, we just substitute. What's big R? Yeah, big R is y sub 1, little r is y sub 2.
Oh, I see. Okay.
Yeah.
So
the integration is fairly trivial. Well, maybe, it's not quite so trivial. In other words, we're going to integrate sine squared of x dx minus the integral of 1 minus cosine x quantity squared dx. And you'll notice, first of all, integrating sine squared is not so easy. You actually have to use the power reduction rule. Sine squared of x, I always miss the sign on this. I'll see if I can do it based on memory here. Let's see. That is the integral of, let me think for a second, the power, it's, I believe, 1 plus cosine of 2x all over 2. I think that's what that converts to. Power reducing. Sine squared is 1 minus. Cosine squared is 1 plus. That's where I always miss it. And, no, this will work fine, yeah. Now, you see why we can integrate this and we can't integrate that?
Let's see. Oh, because it's, well, you have to multiply out the terms, wouldn't you? And then.
Well, if we're dealing just with this at the moment, in other words, is all I've done is change sine squared into this. Sine squared is the same as 1 minus cosine 2x over 2.
I thought that was the integral of that. Okay.
No, it's actually the identity. In other words, we don't have any way of integrating that. How do you integrate sine squared? You can't use the power rule because it would require there to be a cosine x next to it. So if we use the power reducing rule, now this turns into the integral of 1/2 minus the integral of cosine of 2x, and then I can even take that 1/2 out like that. And we know how to integrate cosine of 2x. It's sine of 2x divided by 2.
Okay, so this is,
yeah, let's take this left side all the way to the end. In fact, let's take it all the way to the end as review. So we've gone from this step to these two integrals. One of the key things of integration is if you can turn multiplication into addition or subtraction, that goes a long way towards solving the problem. Notice that we started with multiplication. This is the integral of sine x times sine x. That's what makes it so hard. When we turn that into this identity, now we're doing the integral of two things being subtracted.
Yeah, that makes sense.
Yeah, so the integral of this part is 1/2 x, and the integral of this part, there's the 1/2 that's outside, and the actual integral of that is sine of 2x over 2. Notice that if you take the derivative of this, you get this.
This was cosine squared of x, and then that led to, wait, no, it was cosine of 2x. Yeah, that's all.
Right, that integrates to sine of 2x over 2.
Okay, right.
And by checking it, if you take the derivative of this, well, the derivative of sine is cosine, so it would be cosine of 2x divided by 2 multiplied by the inside derivative, which is 2, taking out this 2 from the denominator, leaving you with cosine of 2x. Okay? So by differentiating this and getting this, we know we've done the integral right. Okay? And that's just this part. Okay? But we're at a point now where we can evaluate this pretty good. We have to evaluate it from 0 to 2 pi, so there's no difficulties there. Let's do the integral of the other half.
Oh, we're going to do that one or no?
This one here.
Integral.
In other words, remember the problem is it's the integral of r squared minus little r squared. Well, big R is sine x, little r is 1 minus cosine x.
So now we're doing the right side.
And there's a pi out in front here too. In other words, I removed the pi. I forgot to put it. Part of the problem with removing the pi is you forget to put it back in sometimes. There. That's the left side only. Okay? So now let's play with this thing over here on the right. Again, we've got to square this. So what's 1 minus cosine x squared?
Okay. 1 minus cosine x squared. Well, are we just multiplying it out?
Yeah, we're just doing a binomial squaring.
Oh, I got you. So it'd be, okay, 1 minus 2 times cosine of x times 1, just cosine of x, and then times cosine squared, or plus cosine squared of x.
Okay. And again, this is easy to integrate. In other words, we're looking at the sum of 3 integrals, if you like. I can actually put integral signs there. Okay. This one integrates to x. This one integrates to sine of x. And this one, we need to apply the power reduction formula. In other words, I need to erase cosine squared x and replace it with 1 plus cosine 2x all over 2. And now I can integrate that quite easily also. When I say easily, I mean it's not a difficult integral. The most difficult part of this problem is keeping track of your pi's, your negative signs, and how many terms you have. You'll notice that just doing the left side produced this whole thing. Doing the right side is going to be even worse, because doing the left side I just had to integrate this. Doing the right side, I got to integrate this, I got to integrate that, and I got to integrate that in 2 parts. So I actually end up with 4 integrals on the right, 2 on the left. So to actually solve this problem, I have 6 integrals.
Wow.
Yeah, because this turns into 2 integrals, and this turns into 4 integrals.
Right. Oh, 4?
Yeah, because this third one actually turns into 2, because you have to, in order to do this integration, you have to separate it into 1/2 plus cosine 2x over 2.
Okay. So that's I see. Okay.
And let's just double check, make sure that they've, and I'm not really concerned with the final numerical answer, but I do want to make sure that I've set it up all correctly. So, let's see if I can find where this is. I sure didn't title these very well. I think it's the next page. And that was the first question, so it must be the page next. Okay, 2, yeah. So, to figure out the area of the shaded region, we had from 0 to pi over 2 of that minus that. Okay, we got that. For B, the interval of integration from part A, the volume is, take the pi out, sine x squared minus that squared.
Yeah.
They didn't go into detail because this is the calculator part of the test. You could actually just input this directly into Wolfram Alpha to get a number. The only reason I went through it is because it is kind of an interesting integration problem, because it requires you to use that power reduction to actually do it.
But what was the on the right side? We didn't finish the. We had to integrate 1/2 plus cosine.
The right side was this. I didn't bother to go through and actually do the integration. Well, I did it for this, and I did it for that. And now to integrate this, you're going to have a 1/2 x plus sine of 2x over 2. And we're going to evaluate that from 0 to pi over 2. So now I've done all 6 integrations.
Would that be, and when you integrate the cosine of 2x over 2, oh, I was thinking it was differential. No, yeah, okay. So it's sine of 2x.
Yeah, if you differentiate that, you get that.
Okay. Yeah.
I may have left out a 1/2 even. I think I did. I think this is going to be 4, yeah. And I left out a pi. I'm going to multiply this whole thing times pi. But basically, here's our 6 integrals. There's the result of the first integral, the second integral, the third integral, the fourth integral, the fifth integral, and the 6th integral.
I can tell, like, my basic integration and differentiation skills are like atrophying, I think. Or
well, that's a problem. It's a problem I face too. I'm really quite frightened. I'm sure glad that you and I are doing this, because I would be in serious trouble. I mean, I know what happens. I used to play the piano very well, and the moment I lost that piano, a year later, I didn't know how to play a note.
I got you.
And so I know that if you don't practice stuff, you're going to forget it. And it's been a long time since we've reviewed some of these basic integration and differentiation stuff. So, yeah, I still don't have a calculus student other than you.
No kidding.
Yeah, it's
that's really amazing.
It is amazing. I don't know. It's got to be purely random. I mean, I suppose. I mean, usually I get new calculus students. It's not purely random in the sense that any student I had last year that was pre-calc and not a senior should be taking calculus this year, and they would be using me. So I must not have had very many pre-calc students last year. I have a bunch this year. I have about 10. And they're all less than seniors. So I should have plenty of calculus students next year.
That's what it is.
Well, it's that combined with, I don't know, in a typical year I might pick up 5 to 8 new calculus students. And hold on, my TV just came back on. Let me go turn the sound down. 1 second. Interview with probably another movie you have there. I Am Alice. Julianne Moore was nominated for Best Actress from that movie.
I don't know if we have that or not.
Plays a woman that early Alzheimer's. She gets diagnosed at age 50.
Oh, my mom read a book recently called like Still Sadie or something.
Yes, I think it's the Still Alice. That's the title of the movie. Still Alice, I think.
I wonder if they made a movie out of that book.
I bet they did. In fact, it seems like your mom and I talked about that when I was there last. I thought I made a comment about that, and she mentioned that, but maybe not.
She told me she was reading that book.
Yeah, and I'm not sure that would be the funnest book to read, especially at my age.
Yeah.
But, I don't know.
Oh, Dave, while we're talking, would you show me Part C so I can know what it was? So for next time, maybe I can know what it is, have it down.
All right. Concept of Part C is, let's say we want a paperweight.
Yeah, I can't quite see the C part.
Okay.
It's a little bit.
So Part C is saying if we wanted to use area R as the base of a paperweight and the height of the, in other words, how far out it comes, is equal to the square of the length of the base. In other words, hold on.
Base R.
Yeah, we don't need to solve it today, but we can set it up. In other words, here's my picture. The height of this paperweight, this is just a two-dimensional bird's eye view of it. The height is the square of the length of the base. In other words, we're going to put cross-sections like this on top of the paperweight, and the height of those cross-sections is the square of the difference of the functions.
Base R. I see. So the base is just the area R. And then you have jutting up from that,
Yes.
you have...
Yes.
Okay.
This would be called a mathematician's paperweight because it would be a very unusual looking object. In other words, the height above the paperweight right here is the square of that difference. The height of the paperweight right here is the square of that difference, which is smaller. So you don't have a uniform height. You have a very odd-looking paperweight.
I see. That is a function.
And so if we wanted the volume of that paperweight, we're going to need to sum up the volumes of each of these cross-sections. We're going to do it, the skinny side of the cross-section is along the x-axis. So we're going to do that. And then the square of the length of the base is that function squared. In other words, y sub 1 minus y sub 2. And let me think about this for a second. That would be the height of that rectangle, or I should say of that rectangular solid.
That's the entire thing? Okay, you're doing the whole...
I think that, yeah, in other words, if I want to find the volume of that particular piece, that slice of this thing, I'm going to take the, first of all, I'm going to take its base, which would be the difference of the two functions, and I'm going to multiply it by its height, and they're saying the height is equal to the square of the length of the base. So it looks like I would be cubing that.
Whoa.
In other words, if the base of each of these things is y1 minus y2, and the height of each of these things is the square of that, y1 minus y2 squared, which is what I read that to mean, and the volume is the base times the height times dx. So it looks to me like base times height would be y1 minus y2 cubed.
Yeah, so, yeah, the height was that whole thing squared, right? So, yeah, so the volume... Yeah,
Compute the volume of the solid with base r and height. The height is a function of the two functions. Yeah, it clearly says the height equal to the square of the length of the base. Well, here's the height. The height is the square of the length of the base. The length of the base is y1 minus y2, so if the height is that squared, that's the height.
How does the absolute value come into this? Does it matter?
Well, I didn't throw that in because it's clear that the top function is always bigger than the smaller function, so I don't know why absolute value is needed. Certainly, if you were to continue this on and this crosses over and becomes the top function, then you'd want to use the absolute value.
I see what you're saying.
In this case, sine x minus this is always a positive number.
Right.
And even if it wasn't, the fact that we're squaring it is going to eliminate. Even if this was negative, it won't matter. It'll turn positive.
I wonder why they felt the need.
Yeah, exactly. In other words, that since if they'd have made it the height equal to the length of the base, then I can see the need for the absolute value sign. But when you say the height is equal to the square of the base, I don't see the need for the absolute value sign.
I got you.
And if you were integrating the absolute value of y1 minus y2, the moment you square that, you take away the absolute value sign.
Yeah, I see what you're saying. No point to that.
All right, we can talk about that more next time and check their answer and make sure that we did it right.
Sounds good.
All right.
Yeah. All right. Well, thanks so much,
Have
Dave.
a good week. I'll talk to you next time.
Yeah, I'll try and get that Pie movie.
Okay, sounds good.
For some time down the line.
All right.
All right, Dave. Thanks so much. We'll talk to you soon.
Bye-bye.